My pleasure to welcome everyone to the annual Emilio Segrè Lecture. Since 1987, by the way, my name's Steve Boggs. I'm the chair of the physics department here at Berkeley. Since 1987, Berkeley Physics has had the opportunity to bring world-renowned scientists to our campus to speak in honor of one of the greatest experimentalists of the last century, Emilio Segrè. The lecture series, which occurs each fall, highlights trends, discoveries, groundbreaking research, and is made possible through the generosity of the Raymond and Beverly Sackler Foundation. Emilio Segrè was one of the 20th century's most distinguished physicists and was one of our esteemed faculty members for more than 5 decades. Together with Owen Chamberlain, he won the Nobel Prize in 1959 for the discovery of the antiproton. He had been a student of Enrico Fermi's in the late 20s and later a professor in Palermo. But while on a visit to California, Mussolini passed a law barring Jews from obtaining university positions, and Italy's tragic loss was America's gain as he was unable to return to his home country. He became a group leader for the Manhattan Project at Los Alamos National Laboratory and eventually a professor here at UC Berkeley in 1946. Today, we're fortunate to have his grandson, Gino Segrè, and his wife, Kate Gordon, with us to also honor his legacy. So Gino and Kate, we just want to thank you guys for joining us. Surprise! Past Segrè lectures have included former Chancellor Robert Birgeneau, Hans Bethe, Herb York, Masatoshi Koshiba, Bert Richter, Mildred Dresselhaus, Andrew Lang, and this year's Nobel Prize winner in physics, co-winner Art McDonald. This year, we're pleased to add to that list Stephen Chu, Berkeley alum, Nobel laureate, former director of the Lawrence Berkeley Laboratory, and former Department of Energy secretary. His lecture, entitled A Random Walk in Science, takes us on a journey of remarkable career, one that started here at Berkeley with his mentor, the late Professor Emeritus Eugene Cummins. Professor Cummins passed away last month. It was a very sad event in our department and on campus. He left his mark on the campus and with his students as a scholar, extraordinary educator, and esteemed colleague, and he will be deeply missed. Today, his wife, Iris, and his son, David, are with us, and I want to just thank them for joining us. Iris and David, could you please stand up for a second? Thank you both very much for joining us tonight. And now, let me actually introduce our speaker, Stephen Chu, who's joined by his wife and our good friend, Jean Chu, tonight. Stephen Chu is the William R. Keenan Jr. Professor of Physics and Molecular and Cell Physiology in the Medical School at Stanford University. His research spans atomic physics, polymer physics, biophysics, biology, biomedicine, and batteries. You're making us all look really bad, Steve. He shared the 1997 Nobel Prize in Physics for laser cooling and atom trapping with Claude Cohen-Tanuji and William Phillips. He received degrees in mathematics and physics from the University of Rochester in 1970 and a PhD from UC Berkeley in 1976. Following 2 years as a postdoctoral fellow at Berkeley, he joined the AT&T Bell Laboratories in 1978 and in 1983 became head of the Quantum Electronics Research Department. While at Bell Labs, Chu first demonstrated optical molasses laser cooling, optical tweezers, and the magneto-optic trap, the 3 most widely used methods in laser cooling and trapping. In 1987, he joined Stanford University. He served as the Theodore and Francis Gabal Professor of Physics and Applied Physics, twice Chair of Physics, I feel your pain, Steve, and helped launch BioX at Stanford University, a multidisciplinary institute combining the physical and biological sciences with medicine and engineering, and the Kavli Institute for Particle Astrophysics and Cosmology. In 2004, he became the director of the Lawrence Berkeley National Laboratory, rejoining us here in Berkeley. And then in 2009, he stepped down to become the 12th US Secretary of Energy, a position he held until the end of April 2013. He is the first scientist to hold a cabinet-level position and was the longest-serving energy secretary, recruiting numerous outstanding scientists and engineers into the Department of Energy. After completing his government service, he returned to Stanford and is currently doing research developing new nanoparticle probes for optical imaging and their application to studies of live organism imaging in neurobiology, cancer signaling, and biofilms. He is developing next-generation batteries and other applications of nanotechnology. Holder of 10 patents, Dr. Chu has published over 260 scientific and technical papers. In addition to the Nobel Prize and numerous other honors, he has been awarded 25 honorary degrees. He is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, National Academy of Inventors, the Academia Sinica, and a foreign member of the Royal Academy, the Royal Academy of Engineering, the Chinese Academy of Sciences, the Korean Academy of Sciences and Technology, honorary fellow of the Institute of Physics and of the Optical Society of America. We are thrilled to now add Segrè Lecture to that list. Please join me in welcoming Dr. Stephen Chu and thanking him and his wife for joining us tonight.
Thank you very much. It is truly a pleasure to be here and give the Segrè Lecture in honor of Emilio Segrè. To visit back at Berkeley, and I've spent many happy moments here at Berkeley. I also want to mention my advisor, Gene Cummins, who, well, I can't really say much. I'm going to get all goofy. So anyway, so I'll just move on. All right, so let me plot out. This is a kind of a confession of a career, a very checkered career, and to the younger people here, you know, there are milestones in a person's scientific career. You have a first contributed paper. You give your first invited talk. You're going up in scientific standing. Then you're asked to give a first plenary talk. And then, because of great inflation, they have something higher than that, and it's called a keynote. And then afterwards, something begins to happen, and you start to give after-dinner talks. Okay. And then you begin to talk about other people's work at after-dinner talks, going further downhill. You begin to mess them up. Giving after-dinner talks, and then you become a bureaucrat who speaks at ceremonial occasions. All right, now I want you to notice something. There's an axis to this, and that's 0, and you can go negative. And when and you begin to reminisce about the good old days, but you butcher the history. So this is a butchering of some history. All right. So let me talk about random walks. You know, life is a series of random events, many random events. You don't really able to choose your parents with any authority. And let me give you an example. This is a picture of my mother and father on their wedding day. It's 1946, and you look very handsome couple. And talk about a random event. How could you ever imagine they could have a baby like this? So, and it's just not a bad hair day. All my baby pictures look like that. Okay, so I'm going to fast forward and talk about my time at Berkeley and in the Gene Cummins group. University of California, Berkeley, when I came in 1970, was spectacular. There were 9 active Nobel laureates in physics and chemistry. There, if you count Macmillan as in physics, and you know there were 6 in physics. And I love this picture because you can actually see LeConte and Burge Hall. And so that was also spectacular. What I didn't realize while I was there in the 70s, that Berkeley had some graduate students who went on later, and these are the times of their PhDs in chemistry, MCB, and physics to get Nobel Prizes. It was an amazing place. So I joined Gene's group. Gene had had some spectacular experiments in time reversal invariance, but he always had a very small group, and those people were leaving. And I overlapped with a couple of people. One was Stuart Freeman, who was a faculty member here for a very distinguished faculty member. And that's Stuart on the left, and Mel Simmons on the right with the T-shirt acting deputy head. And they were kind of like the Bobbsey twins. They were inseparable. And the three of us shared an office together. And I was this young kid, and they were, leaving. And I would always have a messy desk, and it would just sort of spread out onto the communal table. And it got so bad that Stuart laid down a piece of black tape on the floor and on the desk and said, "Your space, don't go any further than this." And so that's what happens with senior graduate students and junior graduate students. So let me tell you, so I began to work with Gene. The first quarter I took a class from him, and he was an inspired lecturer. And since that first quarter of that first class, every class he taught, I would make sure I would take it. But I started out, and he actually assigned me a theoretical problem, of protostar formation, not what he was doing, but he wanted to move into astrophysics. And I worked on that for 3 months, and I got it incomplete. After a few months, I would sneak into the laboratory and do play experiments. And finally, I told him, "Gene, I think I want to be an experimentalist." So he kind of looked at me and said, "Oh, okay." And so he said, "Well, there's this beta decay experiment, and maybe we can do something there." I worked on it for a year with him. By then, he became chair of the department, and this was at the 88-inch cyclotron, and it went nowhere also, so I got another incomplete. Then, he said, "Well, you deserve something better than this experiment, so we'll go looking around." And at that time, I said, "I'm really like lasers, dye lasers." This is in the early 1970s, 72, and I was talking with some Ron Shen students, and I said, let's do an experiment with lasers. And I don't know anything about lasers. Don't worry about it. We'll just do an experiment with lasers. So he found one with Richard Maris, the Lamb shift of high Z, and so we worked on it for about a year, and got another incomplete. All right, so what was happening? So what was happening in the late 60s and early 70s was something spectacular. There was a proposal of unifying the electromagnetic interactions with the weak interactions, which are described radioactive decay. And Weinberg, Salam, and Glashow had proposed in the course of 67, 68, and a little earlier with Glashow's work, that it may be possible to make this a single unified theory. Gene was an expert on weak interactions, beta decay. He had written a textbook, and so I said, "Well, what about this?" And he said, "Nah, it's just a speculation." But what changed his mind was in 1972, other individuals, Tuft and Veltman, showed that some of the ills of the previous Fermi theory could be curable. And so he said, maybe there's something there. And then Marie-Anne Bouchiat and her husband, Claude Bouchiat, published a paper in 1974 that suggested maybe you can see the effects of this new theory in atomic physics. And okay, so I read the paper, Gene read the paper, and we decided we're going to stop what we're doing, just stop completely, and work on this. And so there I was, a graduate student, 3.5 years, starting my 4th experiment, and it was, so I worked on this for 2 years. Then Ralph Conti joined a little bit later, and after 2 years, I went to Gene and I said, I've been a graduate, so I'm going on 6 years. I'll make you a deal. Give me a PhD, and I'll stay, and I'll finish the experiment. he kind of looked at me and said, okay. I said, oh, I suffered enough. No. Anyway, and so it was actually good for him because I was an NSF fellow, but the last 2 years, they only give it you 4 years. And as soon as I became a postdoc, I could be an NSF postdoctoral fellow, so I became free again. So it was beneficial. All right, so during that time, I started building dye lasers. This is me before the phase change. I had a lot more hair and looked younger. And so, and in this picture, there's a picture of a gizmo thing, which was a dye laser that I had built up. And it worked very well, but that's okay. We needed a workhorse laser. You simply couldn't buy it. All right, so my PhD thesis was not parity non-conservation. We couldn't get there. So it was a measurement of the precursor, just the atomic transition. And so if I had to give myself a grade, it would be a C. And this is now finishing my 6th year as a graduate student, okay? And so we were all excited. We thought this was a great piece of work. We submitted to PhysRev letters. It was rejected and said, you're not measuring parity non-conservation, so we're not going to publish it. So, all right. Okay. So 1.5 years later, in the spring of 1978, Gene says, we'd like you to apply as assistant professor at Berkeley. So I said, oh, really? I published one paper. One science, I published, okay. And I said, well, yeah. And so I had a job talk. It was in the physics department cloaking. There were about 400, it was like 1 or 2 LeConte, I forget which one. There were 400 people. And I remember going before, there's another researcher named Mike Pryor. He said, let me give you a warning. Well, I got 2 warnings, one from Gene, one from Mike Pryor. He said, Emilio Segrè will be in the audience. And so make sure you know what you're talking about. Because he might raise his hand and say, I remember Enrico and I were thinking about this long, long ago. So I said, okay. All right. Gene Cummins gave me, he says, I'm not going to tell you what to say or what you're going to talk about, but I give you one bit of advice. Whatever you do, don't give the lecture in tennis shorts. Because I would always walk around in tennis shorts. Okay, so they decided to offer me an assistant professorship. I took the job. They gave me $25,000. I spent it that early summer to buy a dye laser system and a pulse YAG laser system, okay? So, and then that fall we submitted another paper. I'm there down in the author list. This is now Ralph Conte, Phil Buxbaum, me, Gene Cummins, and Larry Hunter. And Gene was great. He said, now, I know you really did a lot in this experiment, but you have a job. So I'm going to put you far down in the author list. So I said, I don't care. And so he was looking out for the next person. That was very classic of Gene. And so that was fine. This is what I look like. This is with some Polaroid camera that Percy Drell, she was beginning graduate student at her first year, and I worked her for the first summer where she began research. Now I want to draw your attention, you probably can't see this, but in the background, there's a crop picture of someone, it looks like a little baby with a noose around the neck being hung. And it's W.C. Fields. And so this is Gene's idea of humor. So he would put up artwork, strange art like this. And he loved W.C. Fields. This is the laser Persis and I built. So we spent the summer machining these parts and building it up. But I want you also to notice something. I'm going to now change the contrast of this thing. By the time I was supposedly entering an assistant professor job, I didn't really know much physics, but I knew how to build lasers, and I knew how to scrounge stuff because we were too poor to buy a lot of this stuff until my starved money. But there's another thing that Gene added. We build a laser, we punched a hole through the wall, the laser light goes in the next room where the experiment was, and so Gene decided to decorate the hole. And so he actually put up this clown's face. That's all Gene. Anyway, so that's one of his terms. So in my 8 years I learned from Gene, I learned a couple of things. I learned that it's really important to work only on fundamental questions, that it's okay to change course and abandon what you're doing before completing it, and it's also okay to stick with it for a long, long time. So I was the first student, and then Ralph, and then Phil Buxbaum, and then Larry Hunter, then Persis Drell, all working on the same experiment in various generations. The first one was really lousy. I can tell you our result was really stinko, my result. Or the first generation, and it got successively better. Also, the importance of writing clearly. Those of you who don't know, Gene's father was an editor. His name is Sax Cummins, and he was an editor of, I think it was from Random House. And Gene Cummins was Eugene Cummins because his godfather was Eugene O'Neill. And he was an editor for Eugene O'Neill, but he didn't talk much about Eugene O'Neill. Gene did talk about William Faulkner a lot, who's another person that they had a house in Gene's family in Princeton, and he said that Faulkner would spend weeks at a time writing upstairs in the little loft. He would come down and he'd give on the kitchen table 3 pages of manuscript, and I said, and what do you tell Faulkner how to write about? And he said, well, you know, character development, this and consistency. And so Sax Cummins would make corrections and leave them on the kitchen table because Faulkner was sleeping during the day and writing at night. And to make sure the breeze didn't blow away the pieces of paper, there was a bottle of bourbon on top of it, a new bottle, and every morning there was an empty bottle. And some more pages. But Gene's writing style was very spare. It's more Hemingway-esque. But he really appreciated good writing. I wrote a thesis. I wanted to get it done really quickly, so I wrote the first draft in 2 weeks. I gave it to him, and I said, well, let me go back into the lab. And he kind of looked at it. Instead of just calling it with red marks, he just gave it back and said, you can do much better. And just gave it back and said, be more precise, let the reader know exactly what are the ideas and what was done. And just handed it back. And so 2 weeks later, I gave him another draft, and he said, that's okay. And then he let me back in the lab. Now, Gene was a master at taking a known technology, atomic beams, and improving upon it and driving it to where you wouldn't believe it, and with exacting rigor and systematic effects. He was so good at that stuff. And I couldn't really figure out, is this my strength? And what I learned from other professors at Berkeley at the time was that if you're going to do something and you're not as smart as Gene, a lot of professors were very, very smart. Charlie Towns would invent a new technology and apply it to a new field, astronomy. Ron Shen, nonlinear optics. John Clark, interference in squids. And all it. So from these others, I began to realize that there's another way of doing science. And to maximize your ability to make new discoveries if you're not that smart, invent and develop a new technology and to be the first to apply it. And otherwise said, if you're the 100th person to look at the same problem with the same tools, you'll probably not find anything new. So I learned that from the other great scientists at Berkeley, because actually I was not like Gene in that respect. I was kind of goofy. Okay, so then I went to Bell Labs as a leave of absence. It was amazing because when they gave me the appointment, they said there was a lot of discussion. You spent your whole time here working on one experiment, and we want you to be a faculty member here. You're welcome to start your own group and do whichever you want, but you're also, you can take a leave of absence for 2 years, go anywhere you want, but you're a faculty member and you And I said, great. So I decided to go to Bell Laboratories for 2 years. And so at Bell Labs, another very checkered past, I worked with 2 former Berkeley students. Hyatt Gibbs was a student at LBNL and a postdoc with Gene, and Sam McCall, who was a student at Irwin Hahn. And we worked on some problem. Phil Anderson at Bell Labs had just gotten a Nobel Prize for what was called Anderson localization. And he said the only real proof of this was this one experiment done in optics. And Hyatt said to me, you know, I know you want to do other things, but why don't you join us and figure out, you know, you can strengthen the claim. And so we worked in this energy transfer, and after a couple of years, we found that the system didn't even apply to Anderson localization. And it was not a null result, it was a result that said the first set of experiments were incorrect. So, all right. Then I worked on laser spectroscopy of positrons and electron and its antiparticle, something really in the commercial interest of AT&T telephone company, with a fellow by the name of Alan Mills, and later Jan Hole joined us. It was a good experiment, and ultimately we were able to make a precision measurement of a few parts in a billion, but it went nowhere. Well, you know, it got some notoriety, but in terms of science, it went nowhere. This is what I looked like at that time. Laser cooling and trapping of atoms, I started to work on, and that actually worked better than expected. So I'll spend a little time on this. So here's the idea. Suppose you have an atom and it's going in a certain direction, like to the right. And if you know it's going to the right, you can take a laser, scatter photons, particles of light on it, and you can slow it up. But what if the atom is going to the left? This will not slow it up, it will accelerate it. And so this is a problem. So if you know which way it's going, you can slow it up, but to cool something, you're taking out the random temperature. And so the idea was that you put another beam on the opposite side and use what's called the Doppler effect. And so the Doppler effect is the following. If you're an atom and you're moving towards the laser beam on the right, I'm going to move towards you. And as I move towards you, my voice goes up. And I move away from you, my voice goes down. So if you tune the laser so that if the atom's moving towards the beam on the right, it goes more into resonance, more likely to scatter. It's running away from the other beam, less likely to scatter. So that was the idea. If the atom goes in this direction, you can use 2 or more laser beams. And this was a wonderful idea. It was too good to be true. I couldn't believe this. This is amazing. So I told I was then a department head at Bell Labs, and I went to my boss and I said, this is going to be amazing. And he kind of looked at me and said, because you can maybe trap atoms once you get them cold. And my boss was Chuck Schenck, who was LBNL director for 15 years after he was at Bell Laboratories. And he had shut down the program 4 years ago. So I said, okay, you're allowed to do this. Don't try to talk anyone else into doing it. Okay, so I said, fine. And then at the very end, the last couple of months, I said, hey, psst, it's gonna work. So don't bother, we don't have to ask permission. So it was gonna work. And so from the time of this quote, rediscovered the idea, to the time I sat down to write the first draft, it took 10 months, and I didn't have a vacuum chamber. The whole experiment was 10 months. So I did, and then Ari Ashkin says, you should read this paper because it has something with what you just did. I read it, it was the Shallow-Hench paper, and I said, oh my God, it's everything I did, so it was a reference 1. So it worked very well. We got atoms very cold, but I messed up here too. Because there were early signs that they might have been colder than theoretically expected. I kind of ignored them, I put in big error bars. And then Bill Phillips and his colleagues remeasured it because there are nagging signs, and they said, holy smokes, it's the minimum temperature, expected temperature was 240. Oh, that's not Kelvin, it's microkelvin. Apple to PC to Apple. So it's millionths of a degree above absolute zero, and so it worked much better than theory led us to believe, and so you call this a strong violation of Murphy's Law. All right, why is it working so well? And then it was clear that the theory was just a ground state and excited state of an atom, so there must have been something in there because it was a complete QED theory. And so there was a little bit of scrambling, and within 6 months, Jean Dalibard and Claude Cornugy and I independently figured out the quantum mechanics of this. And that was done in '88. All right. So a lot of things happened at Bell Laboratories, trapping of atoms, the magneto-optic trap, all those good things. But then I decided perhaps I should go back to academia, and so I had to decide between Stanford, Berkeley, and Harvard. And Gene, again, said his recruiting style was subdued. And he said, why are you even considering Stanford? Because instead of being a big fish in a small pond, you can come to Berkeley. And he was right. At the time, Berkeley was heads and shoulders above Stanford. Stanford was a very small 22-person, 21-person department. They had some really good people, but they were either dying, retired, or about to retire. And so in the next 10 years, 40% of the faculty would turn over. And I said, so I rooted for the underdog and decided to go to Stanford. Now, you might be asking yourself, why would you be interested in cooling atoms to these ridiculously low temperatures and holding on to them? And I have to confess, when we first were able to cool and trap atoms, I went up to a former director, my former boss, Bill Brinkman, and I saw him in a meeting. He said, Bill, guess what? We cooled and trapped atoms. And he knew I was very excited. And he said, Steve, that's great. As a good manager, you never want to, dampen someone's enthusiasm. Then he said, and what are you going to do with it? And I said, Bill, I have the foggiest idea, but it's really neat. So this is a big departure from Gene's training. It was not a fundamental question, a deep thing. But nevertheless, let me tell you one application I knew about when I was at Bell Laboratories. You can make a better clock. Oh, what does that have to do with anything? So when I got to Stanford, we did the following. We took this ability to trap atoms, you get them really cold, and you can toss them up, and they can turn around due to gravity. And in the time they're in free flight, turning around due to gravity, you have a long time to make a measurement. And so with that, I said, okay, this so-called atomic fountain will make a better clock. The NIST people, the French group got into this. Very soon we did a second experiment in cesium, and we exceeded the short-term stability of the clocks. Within 7 years, contributions all around the world, the atomic fountain became the time standard. And so a very, very short time from the time you first do a demonstration experiment to it's the method. Now, a lot of water has passed under the bridge since this time, 1989. There are now optical clocks using cold atom technology that are really going to surpass anything you could dream about in the microwaves. And I'm pretty confident they're going to achieve an absolute accuracy of 18 decimal places. What does 18 decimal places mean? If you had a clock when the universe was born, and you asked today, 13.8 billion years later, what time is it? You would know within a fraction of a second how much time has been spent. Now you're asking yourself, you don't need that accuracy. Aren't you just showing off? And the answer is, of course we're showing off, but not really. The most precise measurements in all of science are frequency or frequency shift or so-called phase shift measurements, which is the best way of measuring frequencies. And for that reason, the length is defined in terms of time. How far does light go in a certain number of oscillations of a cesium atom? The volt, the ohm, because of wonderful quantum mechanics, also can be defined in terms of frequencies. And the most accurately known physical constants, for example, Planck's constant by the mass of the atom, which will lead one to the fine structure constant, could also be measured this way. And the most sensitive tests of fundamental symmetries, like time reversal invariance, or looking for an electron dipole moment, are actually phase shift or time frequency phase shift measurements. And in fact, Gene Cummins spent his second time after the parity stuff, and he went back to time reversal, and he pushed that technology even further. And so, Gene and his group held the record for the best measurement of whether an electron has some structure. It's just not a point particle. Succeeded only recently by a former student of Gene's, Dave DeMille, and John Doyle at Harvard. And this measurement is so exquisitely precise that it's setting very stringent limits on whether there could be supersymmetric particles that may or may not be discovered at the Large Hadron Collider in CERN. So it's one of those, another amazing things of very, very fundamental science that can be done in a laboratory. But let's go back to the goofy stuff. So when I was at Bell Labs, Art Ashkin used this focused dipole trap to trap bacteria, and he was going great guns, and he could move them around, and he could do all sorts of things and torture them. And when I got to Stanford, I said, is it possible, well, we can trap atoms, we can trap bacteria and stuff within protozoas. So is it possible to hold on to a single molecule by gluing a little sphere? The handle was that little sphere, and in a focus beam. And so you're going to see a movie of that bright sphere is a little polystyrene sphere held with an optical tweezer, focused by the optical microscope, and where the laser is focused, it can be moved around with a joystick. And this is what you can do. So that line of light is a single molecule of DNA. And to my graduate students, it was like playing computer games. And this is what they did for hours and for days. And they were thrilled by it. And I finally said, okay, guys, I know you're having fun, but we should do some experiments. All right. All right. So I should also say that as I was going into biology, a high-energy theorist came to me and said, you shouldn't do this. And I said, well, why not? And I said, because the laser cooling and trapping of atoms is gaining real momentum, and if you go into biology, you might be written out of the history, so you should stay in physics so they remember your scent. He actually said it that way. And I said, nah, I don't think so. So I was doing physics, to be sure, but I was going into biology. Now, luckily for me, so this was all done starting in 1990, 91, 92. Fortunately for me, they did remember my scent. This is Gene Cummins with my mother. They're looking, Gene is kind of listening to her. My mother's a very talkative person. And my mother was saying, you know, he never listened to me. How did you get him to listen to you? But Gene is very quiet and diplomatic, didn't say anything. But this is probably what he was thinking. What makes you think he listened to me? Okay, so this is December 1997, Nobel Prize ceremony. This is a co-winner, Bill Phillips. Physicists are, it goes physics, chemistry, medicine or physiology, literature, pieces given in Norway. And the physicists are always, since it was mentioned first, they're held in the highest regard formally in the ceremony. And the physicists get to sit next to the king and queen, so this is Bill Phillips with the queen. And so, did I feel bad about that? Not really. I get to sit next to the crown princess. Anyway, so now, so I'm going along. We're doing lots of things in physics and biology and atom interferometry. Things are going well, and then Bert Richter says, you know, LBNL is looking for a new director. I think you'd be great for the job. I said, no, I don't want a job. I don't want to be a big... Believe it or not, I didn't really want to be a chair of a department either. But it was a deal that I made from 90 to 93. There were three of us who said, well, there has to be a new generation, and we wanted people to serve the department and not their subfield or themselves. And so I, Doug Ostroff, and Boss Cabrera agreed that we would help each other and we would do it successively. And then it went, and so then that's what happened. And then the next time around, there's no one, so I said, okay, I'll do it again. And then Doug did it again. Boss said, I'm not going to do it again. But that's why it happened. I didn't really want to do this. Chuck Shank calls me and says, you know, we'd like you to throw your hat in the ring. I said, I don't really want to do this. I love what I'm doing in the lab. So he says, look, if there's a 5% chance you might consider it, come and look around and go for an interview. If it's less than 5%, forget it. So I thought, by this time, this is 2004, I thought, I really was getting interested in the last, since 1998 to 2000, in climate change. And Berkeley Lab was a fantastic place, and Berkeley was a fantastic place. A lot of Nobel laureates worked at Berkeley Lab. I think 15. But what people don't know, over 30 young scientists, graduate students, postdocs, or first job, career Nobel laureates were trained at Berkeley Lab. 30, over 30. So I said, if I can go there and convince more scientists to do something about energy and climate change, it would be worth it. So I said, okay. So I left, and Stanford, well, I didn't leave. They kept me on the faculty during the whole time as an active member. I had atomic physics still at Berkeley. Holger Muller was the senior person at postdoc at the time. And so, but the biology moved to Berkeley. And then I was thinking, okay, after 5 years, I was going to step down. The people in Department of Energy, not the Secretary of Energy, I got to know very well, and we became friends. But I was getting tired of it, and I really wanted to go back to the lab, so I was going to stay at Berkeley, and I had some labs in the new Stanley building. And so in November, late November of 2008, I get this phone call and said, well, the president-elect would like you to fly to Chicago and talk about a very important job. And so I said, well, I'm not sure I really want to do this. I was going back to the lab, but how important is it? Secretary of Energy? Okay, maybe I'll go. The previous administration, they wanted me to throw my hand in the ring to science advisor, and I said no, for a lot of reasons. But you never, ever want to go as an advisor. There's a huge difference. If you go with budget authority, there's a huge difference. So I went to Chicago, and there's some rented floor space, and I go into this very warm room. I had a blazer on. I don't think I had a tie, but at least I had a blazer. But I had to take it off because it was really warm. And then 2 or 3 minutes later, the president-elect walks in, he goes up to me, and he's also, but he's from Hawaii, so that's why I think the room was warm. And and so he says, a lot of people are telling me you should be the next Secretary of Energy. And so I stood up and shook his hand and said, who are these future former friends of mine? He ignored it. And so for the next hour, we talked about it, and then I came back, and I was very impressed. I went back and told my wife, if he asks me, I will say yes. And so he asked me, and I said yes. So there I go to the Department of Energy, again, because I wanted to do something about climate change. In research in many things, but here's what was happening in the landscape. This is a graph of the cost of wind energy as a function of time from 1980 to 2000, I think 3 or 4, 2012, sorry. And the cost, the green cost is going down. There was a little blip of supply chain stuff, but it's going to go down. And the amazing thing about wind energy today is in the Midwest, where you have the best wind, the cost of wind energy is actually comparable, if you take out the subsidy, it's comparable to a new natural gas plant, if you assume natural gas is $4 a million BTU, which is, it's $3 now, but historically it's been up and down and up to $12. So that was great. Solar, we have exquisite solar all the way, everywhere in the United States except 2 places, Seattle area and Alaska. And you know, and that blue color means there's not much sun. It's as bad as Germany, which has the highest amount of solar installed in the world. Okay. But the amazing thing is that very recently, the price of solar has come down. So this is a price of a contract. When you're a developer and you put in a big solar farm and you go and borrow money and you build this thing, you won't get any money to borrow, or you wouldn't have anything to do unless you had a utility or a set of utility companies that says, we'll buy it at a certain price for the next 20, 25 years. And in July of 2008, it was going for about 18 cents a kilowatt hour, above wholesale costs by a lot. And by 2014, it was going, these contracts are being sold now for a whole bunch of contracts for 5 and 4.5 cents a kilowatt hour, comparable to new natural gas. Okay? Now, what about deployment of both solar and wind? So here we have not much happened until 1990, and just puttered along, nothing happened. This is installed capacity until about 2009. So then what happened? Well, I became Secretary of Energy. Now, you might say, you might say that correlation does not mean causation. But in this case, that's not true, because I was in charge of a loan program and was skewered for the first loan we gave out, which was picked by career people, Solyndra, and we lost a lot of money, 430 million. That's what happens when you spend too much time in DC. Millions become billions. Anyway. But by 2013, 12 and 13, including all the losses for things like Solyndra, net, the loan program felt that it's going to make the U.S. about $5 billion, including all the losses. Now, I was being skewered for this. I had to personally improve these loans. Most of the loans we gave were to large solar farms and wind farms that the developers could not get Wall Street to loan anything at any interest rate. And so during that time, if you're installing something that's reasonably known technology and you had a power purchase agreement, the only risk is that you would be delayed in the construction and deployment. But once you turn the switch on, you're going to be okay. So all the switches got turned on. And so we also loaned to Ford Motor Company. They were so deeply in trouble. GM and Chrysler had already gone bankrupt and were owned by the government, but Ford was still a viable company. But they were in pretty big trouble. We loaned them $6 billion. We had to set aside $3 billion to Treasury as the loan insurance. So that means $3 billion for that loan meant it couldn't be used in roads or bridges or defense or education. Okay, it was a protection, mortgage insurance, if you will. So we set aside $10 billion. We'll probably lose $1.5 billion, but net, we're going to gain $5 billion. And the loans were being made at 1.5% to 2% interest from 2009 to 2013. Okay, so we weren't doing better in venture capitalists. We were doing better in Wall Street. And at that ridiculous interest rate, because we could have charged 5 and 6 because banks weren't going to loan them for anything. The great news about this is that after that period of time, it's now bankable. You can go out and get loans from Wall Street. In fact, it's turning around that you can maybe get a lower interest loan to build a solar or wind farm than you can to build an offshore oil platform. Okay? And the cost of renewables is the cost of money in large part. Okay? So that was good. Some other things, I'd start a few things. There's a thing called RPE, Advanced Research Projects Agency for Energy. It was modeled after DARPA. It came out of a report that came out, I think, in 2005 or 2000, something like that, called Rising Above the Gathering Storm. Norm Augustine was the chair of the committee. There were 20 people on the committee. I was one of them. And ironically, I was sent by the committee to go to Congress to plead for RPE in congressional hearings. I was sent to the Department of Energy to plead for their support of RPE. Congress gave him support, but the Department of Energy, even though Sam Bodman was a terrific person, the career people didn't want it. So I said, I'm sorry, they didn't want it. But he was concerned about climate. He steps down, 2009, the new administration, Obama comes into office, and the new Secretary of Energy was much more enthusiastic about RPE. And so we started it on Recovery Act funds. And after 2 years, it had enough support, they got base level funding, and actually a lot of Republicans, believe it or not, really liked it. There were other things I did, Energy Innovation Hub, Sunshot. I'm not going to go into this. There were a few things I had to deal with that were unexpected. I didn't really have to deal with this one, but I did. This is the Deepwater Horizon disaster where in the Gulf of Mexico in the spring of 2010, this is a BP, a number of others, and this thing catches fire, explodes. And the Department of Energy has no jurisdiction at this at all. It's Interior, it's Coast Guard, it's a lot of other things. But I made a suggestion to some BP engineers that turned out to be something interesting that I don't know how the president heard about it, but he heard about it, and then after the end of a cabinet meeting, he comes up to me and says, Chu, go down there and help him stop that leak. Okay. So I assembled a team of half dozen other people. I thought of who I was going to consult a few others, called them up. Can you join me? Every one of them said yes, and said, oh, by the way, that's great. Some of them said, I have to check my wife, I have to check the chair of the department, a few other things. They called me back that same day and said yes. This is great. Okay, we have to meet at 8 a.m. the next day in Houston. And every one of them came. And for the next 3 or 4 months, if they weren't there bodily, there were 2 or 3 emails a day, and it was amazing. The cabinet members looked at me and said, Steve, you look really happy. And I said, yeah, I'm solving a technical problem. It was fun, in a macabre sort of way. Lots of pressure. Actually, the new CEO of BP, I kind of bonded because of stressful situations. You can bond, not Tony with the new guy. But this is what it looked like. And CNN had this thing leaking every day. They had television every day. So there's a lot of pressure. I'm not going to go into this, but I just want to mention one thing. That summer, the surface of the Gulf of Mexico was 86 degrees Fahrenheit. Where the oil was leaking out 1 mile deep, it was 2 degrees above freezing. It remains that way all year round. This has to do with climate change because it takes a long time for the oceans to warm up. We don't know how long, perhaps a century, perhaps a century and a half. The damage we've already done, we don't know because we don't know what the new limitation is because the ocean is a cold sink. And only this year, they found out this plateau in the temperature heat-in, about the same, what's going on. It defied computer predictions. They weren't, and we have these buoys that go up and down from the surface of the ocean down 2 kilometers and come back up. Telemetry, their temperature and salinity measurements. There are 4,000 of these, and in 2015, they said the surface temperature was plateaued, just like we knew. But if you average 0 to 2 kilometers deep, it accounts for all the heat. Okay? The ocean mixing increased a little bit, and so the excess heat was going there. Anyway. Okay, I learned a few things in government. The first cabinet meeting, I told the president, I learned a law of motion, that something in motion in a big bureaucracy will come to a screeching halt unless continually pushed. Newton was wrong, Archimedes was right. There was so much friction. If you didn't want something to happen, unless your boss pushed it, you can kill it by just not doing it much. It just stops. But I also learned that how to make decisions, and there are a lot of things I didn't know about. But you've got to make decisions on expert knowledge and knowing what questions to ask. And the other thing I learned after year 1/2 is that you don't be concerned about, quote, tactics. You can be concerned a little bit about tactics, but if you think too hard, it's not going to be good, and so you actually have to make decisions based on some core values. And that helps a lot. Lesson number 2. This is I knew beforehand, but very good people, great people hire people better than they are, and they don't hire assistants, they hire proteges. So in short, A's hire A's and B's hire C's. Because if you're an A, you're not going to be insecure, and you want people around you that are as smart, even smarter than you. And if otherwise, you don't want those types. And what I saw was that you can spot a mediocre manager. They want to brief you. They don't want people below you briefing you. In fact, they don't want the people below them briefing anyone except them. Rather than, they're your proteges, which means you're going to push them out there and talk to everybody. And so a sure sign of mediocrity. Lesson 3, you have to attract and retain the best people. My pitch, I called up a lot of people, friends I knew, got a lot of them to come, and it said, well, look, I know you're going to give up a lot. I gave up a lot, but come join me, even if it's 2 years, 4 years, I don't care. But just come join me, maybe years, because we're trying to save the world. And then a lot of people did have a lot of personal sacrifice. Alum, Rajiv from Berkeley, Rajiv from MIT, lots of people came. I didn't get everybody, but I got a fair number. And you should let these proteges spread their wings. So if I look back in the Department of Energy, it wasn't really the programs I started. You can start a program, but then you hire someone terrific like Arun Majumdar and Dave Danielson and others, and you let them run with it. And mostly you protect them from the rest of the bureaucracy. You own it, I'll protect you. And it was called blocking and tackling. And that's something so that the bureaucracy doesn't drag them down. What I didn't like was dealing with the press. They play gotcha, they're vicious, they're venal. And so when it was decided I was going to step down by my wife, she denies this, but she was great. She came and when we took the job, I had to resign from Berkeley. So it means I couldn't have a faculty mortgage, which means we couldn't maintain the house and have an apartment, so we had to sell the house because no more faculty mortgage. So she decided she was going to come with me. That's great. Hi, Jean. But after 4 years, which every month she'd go back and visit the grandchildren, she said, well, She looked at me and said, "No one's irreplaceable, not even you. So it's time to go back home." And I'm going, so I decided to follow. Where was I going to go? Well, I didn't want to be a president of a university. I didn't want to be head of an institute. I wanted to be a faculty member. So the natural choices were Berkeley and Stanford. But again, because of 4 grandchildren, son and daughter-in-law who were at Stanford, the daughter-in-law is on the faculty in medical school. We went to Stanford, so there was no choice. So I told Stanford that there will be no counteroffer. I'm not going to ask anyone else for a job, and all I want to be is a faculty member. All right, so that was in play in the end of 2008, in late November 2008. I told the president, "I'd love working for you. I'd love to stay another couple of years, but this is what it is. I understand." So we talked another half hour about what I would recommend. So I was allowed to make an announcement on February 1. It was announced that I wrote an open letter to the employees that I was stepping down. On February 7, 6 days later, The Onion runs this story. Hungover energy secretary wakes up next to solar panel. And I'll just read you this excerpts. Sources have reported that following a long night of carousing at a series of DC watering holes, Energy Secretary Stephen Chul woke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, Chul's encounter with the crystalline silicon solar receptor was his most regaled dalliance since 2009, when an extended fling with a 90-foot wind turbine nearly ended his marriage. Now, so I walk in, on February 7 in the morning, I walk in, head of public affairs says, "We don't normally answer scurrilous newspaper articles, but I think we should answer this one." I grin and say, "Oh, yes." So that noon, we issued the following statement. "I just want everyone to know that my decision not to serve a second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar power is a growing source of U.S. jobs and is becoming more and more affordable, so it's no surprise that lots of Americans are falling in love with solar." Now, I have to say also that my wife stood by me on this. She looked at that picture and said, "You don't have hair on your arms." Anyway, back we go, back to Stanford. And during the time I was Secretary of Energy, some spectacular things were happening, actually before that time. And the 2014 Nobel Prize in Chemistry was given to 3 physicists, as it should be. No, sorry. For their development of new methods to push the optical microscopy to new heights. And so this is W.E. Murner at Stanford, Eric Betzig at Genelia Farms, H.H. Mai, and Stefan Hell. Okay, so let me just show you what you would see in an ordinary microscope. This is in the Eric Betzig article, 2006. That fuzzy thing on the left is a section of a cell. That's what you see in an ordinary optical microscope. The thing on the right is this so-called super resolution. And if you blow up that little section, you get something that looks like this. And you can actually locate the position of molecules with about 10 or 15 nanometer precision instead of 250. It's more than an order of magnitude, okay, 25 times better. And when I was at Berkeley, and then I went to the Department of Energy, but I had some postdocs, we were working on this as well. Basil Burke published, and others published a paper in 2012 on this is a single cell, a V colorless single cell, that's what you would see. But this is what you can see in the super resolution, and you blow up that, and you can see that. So the first thing was done on dead cells. This was actually done on live growing biofilms, but it was a rigid cellular matrix. So if you go and look, so then I'm leaving the Department of Energy, and there were a lot of experiments. We in the field of biology, biophysics said there's a lot of things we want to do, but what were the limitations on these super resolution techniques? Well, it takes about a minute to form those spectacular images. It's getting a little bit better. The best images are in dead stuff, and or in rigid cellular matrices, which was that other picture. If it's rigid, it's not moving around due to Brownian motion. And so the Brownian motion would smear it, and you would get no better than optical resolution. So if you can develop nanoprobes that could allow this spatial resolution, not on just 1 or 2 proteins, but on half a dozen, and you can get them bright enough, and other wish lists, maybe that would be cool. So when I got back to Stanford, I started thinking about that. It's liberating. By that time, my group was 0. I let my postdocs take the apparatus with them, so my equipment was 0 minus epsilon. My lab space was gone, my home was gone, everything was gone. My wife was with me, it's good. So whether it was a 10-year sabbatical or a 4 and third-year sabbatical, it actually says you can step back and start something new. So one of the things is, could you put rare earth elements in nanocrystals? And so we started doing this in collaboration with Paul Alvasados, and a graduate student of his, Alexander Cordius, and one of my postdocs. And the idea is, this is neodymium. This is a rare earth that is one of the workhorse lasers. You can excite it at a certain wavelength, and it gives very narrow emissions. And so we started fooling around with this. I'm not going to go into the technical details, but you can put different rare earth elements in these nanocrystals. You can make them 5 nanometers, 10 nanometers, 20 nanometers. You can put neodymium in, and you see light at that green wave, that green curve at 875 nanometers. Ytterbium, redder, thulium, bluer. So let me just point out a few things you can do with this. You have one class of crystals, you put a rare earth in it that you want to label a particular cell or a particular protein. You put, in another class of crystals, you put 2 rare earths in it. Thousands of impurities per 20 nanometer or 10 nanometer particle. So it gives out 2 colors. Or you can put another one that only has 1 color, or you can put in another one that has high in one, medium in another, none in a third. And so you get the idea. Each crystal, you can add combinatorial shades of colors, but it's not a single emitter, it's thousands of emitters. Okay? So you can make a spectral fingerprint for each class of crystals. You try to label a particular protein or a particular cell. And so you can easily work out that there's, dozens, 3 dozen proteins. Okay, if you were labeling cells, individual cells, you can take this image, a microscope objective, where's my thing, and you can project half of it onto where you can center the cells, that's the lower array, and the other side you can put a prism and you can display the prism. So if they're well separated, you can do this. But the real cool thing is, if you're looking for a cluster of proteins within a very small area, like 10 or 20 or 30 nanometers, so within that, what can you do? So let's consider this one cell of this, or with this one protein, a set of proteins within a cell. You want to see them if they're interacting. Because the rare earths have a narrow band of excitation, you can use one laser to excite certain colors, and you can image that. You read it on the camera. You use another laser to excite another rare earth that could be in very close proximity within an optical wavelength, and you read that out, and then you read it out. And so you can start to read out a half a dozen to a dozen different proteins, all within 10 or 20 nanometers. So that's another advantage. A couple of us got excited about this prospect, and so we submitted So the Moore Foundation gave me a lot of money, or not so much money, but enough at the beginning. And then Tom Sudoff, me and Lu Chen Lo said we can do a lot of neurobiology with it. And so we put in an internal proposal to Stanford, and so we got some seed money. And so I can't go into those things. But there's other particles, fluorescent nanodiamonds. This is in collaboration with Nick Blasch and Ziyech Shen at Stanford and Lena Vukovic on the quantum stuff, but it's mostly about growing very small particles of diamond. On the left-hand side, you see these small diamonds. They're a micron in diameter, but they're nearly perfect diamonds. So it's something you can be proud to propose to someone with, because they're really very perfect. We can make them even smaller, and the image on the right is a diamond based on a lot of things, but it's now less than 10 nanometers. So we're making stuff like this. There's some good stuff, there's some bad stuff, but things are happening. Another thing about the rare earths, not the nanodiamonds, the rare earths, they give out the light in hundreds of microseconds instead of in a nanosecond. And remember, you're compensating by putting in thousands and thousands of emitters to make them bright. But so usually you take a microscope objective and you put it on an array camera. But something good is happening. The lifetime is so long, you can put a mechanical chopper in here and spin a wheel. And when you're exciting the probes, the camera is blocked. And then it spins and then lets light through and you expose it and then it closes. But if you work out how good a focus you need, it turns out that you need a pretty hard focus in that center spot, which you can do. But instead of using a metal wheel, you make a glass wheel and you chrome it. And so that is happening. And so my former technician at Bell Labs was the founder and sole owner of Thor Labs. And so he's making us this wheel. He's a great, Alex Cable, he's a great guy. He was so thrilled I was going back to research. I didn't ask him, but he gave $100,000 in my discretionary fund research the first year, and the next year he gave another $100,000. So I'm hoping this is a good trend. So we're working on a few other things with him and others. There's another application. You can take an electron microscope, and electron microscopes give beautiful images of black and white images, but you can't identify specific proteins. Okay, so if you had these probes, these rare earth probes, and collected the light, so normal electron microscope is scanning around. When the spot is at a particular point, you also collect photons. And so these are some samples that Nian Lu made, a postdoc in my lab, and then Peter Mara and Max Priggen and two other postdocs had this bright idea that you can collect different color light, therefore you can identify different proteins, but with the same electron microscope. So again, very preliminary data. The left-hand side is the scanning electron microscope picture of nanoparticles. On the right, this is the color. So it's only fluorescence on the right. Let me remind you, this is a cell. It's a cancer cell called a HeLa cell, and the scale bar is in the lower left, this 1 micron. So this is a cancer cell, but we're going to blow up that little white thing in the bottom. And so when you blow up that little white thing in the bottom, you see the electron microscope image on the left, and that's the electron microscope image, but the thing on the right is the luminescence. But because you can block during the excitation, you actually you can see the cell, but we've already demonstrated you don't have to see the cell in luminescence. You just see the particles. And so we're very excited that perhaps we can get 10 nanometer resolution simultaneous with the electron microscope, but now identifying a half a dozen different proteins. So we're actually doing this work at Lawrence Berkeley lab in a home-built SEM and light collecting, because we don't have that at Stanford. So anyway, at the moment. I'm going to skip this. Go a little bit to batteries. In 2008, the manufacturing cost of batteries was very high. It was $1,000 a kilowatt hour. And then in 2012, it was half the cost. In 2011, we got together in the Department of Energy and said, let's set a goal and a roadmap and see how good batteries can be. And we thought by 2022, if you can get automobile batteries at $160, $150 a kilowatt hour from 1,000, or utility scale storage at less than $100 a kilowatt hour, you would have $100 billion a year market per year. Okay. In fact, the first time in the history of the Department of Energy, we said at what price point, how big the market would be, and we started to make decisions on the applied areas of that. So they thought we were smoking something. You know, it's from Berkeley. Anyway, they also thought the same thing for our solar program, which turned out to, we achieved the goals in the solar much earlier. Okay, in batteries, how are you doing? Well, this is, the blue curve was a projection from Bloomberg New Energy Finance, and the red X's were the manufacturing costs ahead of schedule. If the gigafactory, when the gigafactory gets built, it will, by sheer manufacturing volume, mass production, drop the cost to the goal we thought would happen in 2022. Now, I put the date as when they're going to do this in 2018. The original from Tesla was 2016, but you raised the initial price from what was projected and slide the time back, the so-called Elon Musk factor, and it was still going to be way ahead of anything. It was great. Okay, so energy density was, in per unit volume, was making, you may not believe this, but the battery in your cell phone has 3 or 4 times the energy density of the first lithium-ion batteries that Sony introduced. It's just that display uses a lot of electricity, okay? And so, but the energy per unit weight has only gotten better by 20 or 30%. And so I started working with a professor in material science, Eastway, and the best that you can do was the carbon nanos, which are today's lithium-ion. They're somewhere around this energy density. There are a number of battery companies trying to make silicon with that energy density. And for the last year or 2 years, we've been trying to figure out if we can make a lithium metal with a sulfur in a 3-dimensional geometry. To use nanotechnology, my motto and what I was pushing was the battery has to last longer than the human bladder. What do I mean by that? It's rare that you would drive more than 200 miles without a pit stop. During the time you're having this pit stop, can you recharge the car? You know, charge, discharge. If you have equal time, it's okay. And if you can make it really cheap. Now, the costs are going to plummet, but if you can get this higher energy density, the Tesla battery, well, this is, I didn't correct the numbers. The full weight is about 12, battery pack and everything is about 1,500 pounds. Costs maybe $30,000 to make the long-range Tesla. They're not telling me exactly how much it costs. That's proprietary information, even though I loaned them $460 million, which they paid back early. They paid back in full. So, in any case, we don't know whether we're going to be able to do this, but I know of other smarter people, but there's a whole bunch of people who see this as something that could change the world. Because if you can get a 300-pound battery that allows you to go 300 miles or 250, 300 miles, and the cost is $160, then a $25,000 car becomes without subsidy becomes a reality. And the amazing thing about an electric vehicle is you can have your smartphone and you push the button app and you say, get the car ready. If it's cold in winter or it's hot in the summer, cool it down, warm it up. It calls you back and says, car's ready, we're ready and waiting to go, where are you? In a gentle way. Can't do that with an internal combustion engine vehicle. Okay, so once you have that capability, and you can do this. Yi and I are working on air filters. It turns out that small particulate matter is maybe far more dangerous than we had imagined. And there's papers in 2013, a large meta-study, that said if you have every 10 micrograms per cubic meter of PM 2.5, you have a 1.4 increased chance of getting lung cancer. Okay, and okay, so that's a little scary. If anyone has been to Delhi or Beijing or Shanghai on bad air days, you immediately have respiratory ills of some kind. So where's the number? 10 micrograms per cubic meter, 1.4 higher chance of getting lung cancer. So wherever you see red is higher than 100 micrograms per cubic meter, 10 times more. So the math is you multiply 1.4 10 times. If this turns out to be correct, we will know in a while. How long will it take? About 30 years, 20 years, because it's only been really 10 years since it's really bad. Let me remind you how long it took to do cigarette smoking. This is cigarette smoking, 1900. This is the number of males who smoked cigarettes by the middle 1960s. The average per capita consumption of cigarettes was 220 packs a year, including the non-smokers. Take the whole male population, adult male population, and divide by the consumption of cigarettes, and that's what you get. In the middle 50s, lung disease was a very rare cancer, and it started to grow. And so in the 50s and 60s, the medical community said, what the hell's going on? There may be a correlation or a causative effect between smoking and lung cancer. The tobacco company said, no, correlation does not mean causation. You can't predict who's going to get lung cancer, who's not. I've got a grandmother who's been smoking all her life. She's very healthy. She's wrinkly, but she's healthy. And you didn't understand, and science can't predict who's going to get it and who's not, so this all could be just a chance correlation. Massive education campaign to keep kids from smoking. Smoking goes down. Lung cancers follow, but there's a 25-year lag. It's the same with climate change. The same people have been hired by the fossil companies to say there's correlation, causation. The climate may be changing, but it may not be caused by humans. And what's the problem? And the problem is it's not a 25-year lag. It may be a 100-year lag. And so that is a problem. Now, when you're smoking, the risk is mostly on you. There is some secondary smoke, but it's mostly on the smoker. But the whole world is smoking and fossil fuel, so to speak, and so it remains in the atmosphere. By the way, the women cancer deaths lag because women didn't smoke as much, but they were catching up. So this is another issue, both in smoking, but now PM 2.5, as well as climate change. So I'm going to end this by this image. It's the first mission to orbit the moon in preparation for Apollo 11 landing. And in the last orbit around the moon, the astronauts turned the capsule earthward, and one of the astronauts took this picture. And he said, we came all this way to explore the moon. The most important thing is we've discovered the Earth. So if you look at that picture, the moon is not a friendly place to live, right? And the Earth from that vantage point looks pretty good, yeah, right? And there's nowhere else to go. Now, this was taken in Christmas Eve, 1968, but since that time, we're becoming more certain the climate's changing. There's very compelling evidence that it is mostly caused by humans. Very compelling isotopic evidence that this is not a natural cycle. This is fossil fuel carbon being liberated. And so this is the issue. This is why I took this 10-year sabbatical. And again, a very strange random walk. I'm still trying to work on it. And I think we really have a moral responsibility because the most innocent victims will be the poorest citizens who don't have the means to adapt and people yet to be born. But here's the problem I find. If you're smoking, okay, you bear the risk. So we as a society, if we're not willing to spend half of 1% of the GDP and say, well, we're not really sure. We're not sure what's going to happen. So until we're sure, why should I change my lifestyle? That's not my problem. And it's not, it's not going to be the problem of my children mostly. It'll be the grandchildren and great-grandchildren and people halfway around the world that I'll never meet. So it's not a problem. And so this is bad news. So I would remind you there's an ancient Native American saying, we do not inherit the land from our ancestors, we borrow from our children. One final closing picture. So in this really strange random walk, going away from fundamental science, poking my nose in things and not knowing anything about anything, and just hoping it's neat and cool. So I always looked to Gene for approval. He wasn't so sure about laser cooling trapping for the first couple of years, but I think he came around. And so anyway, I'm hoping he was thinking. Thank you.
Okay. We're going to have people come up and we're going to take a few questions. We only have about 10 minutes, but while people are coming up, let me ask the first question. What
Sure.
did you come to grad school for?
What was that?
What did you want to do when you came to grad school? Was it one of these fields?
No, I wanted to do high energy physics.
You still got time.
And I took a reading course with Gerson Goldhaber my first summer. He was great, wonderful person. And then I thought, Goldhaber Trillium Group, very big. I think there may have been, with collaboration with the SLAC, maybe 40 or 50 people. I don't know, George, you're here. And that was way too big. And so Gene, I was his first new generation graduate student. But that's why when the Bouchet paper came along, there was no question what we wanted to do.
More questions for Secretary Chu?
No, I'm not Secretary Chu, I'm Steve.
Steve Chu? We know you as Steve Chu. Can you come on over?
Oh, come on.
Don't hurt yourself.
Yeah, there's one over here.
When you were at the DOE, did you do any work on nuclear power?
Say that again?
When you were at the DOE, did you work on nuclear power at all?
Yes. You work on all forms of energy, and for those of you who don't know, the Department of Energy is also responsible for the nuclear weapon research and arsenal. But nuclear power was something I personally wanted to see a next generation of nuclear reactors, but I think the safety, the waste disposal, because it gets hard. Once you get, I can see ourselves mid-century 50% renewables. It's hard, it's doable. I don't see 80 or 90% because, bad weather, seasonal changes, all these other things. So we need on-demand power. And if it's half nuclear, half fossil, at least you get rid of the carbon stuff. But it's also economics, whether you can build nuclear reactors on time, on budget, and it's also very local, state generated. California's not going to build another nuclear reactor. Pacific Northwest isn't going to. The Southeast might, if the economics work out. The Northeast won't. There was a question over here somewhere. Yes?
Yeah.
Your hint of the fossil fuel danger for the global climate change is actually more severe in poverty-stricken countries, because public transportation and electricity-based public transportation is lacking. Instead, transportation is heavily based on fossil fuel-based mobile sources. So you are hinting about the cultural change and personal behavior change. Do you have any suggestions on how to reverse the trend of more and more of the population moving to personal vehicles and polluting the environment more and more?
First, developing countries at the first stages of development, their access to energy is directly correlated to economic growth and coming out of poverty. But after that, it plateaus and becomes very flat. And so if you compare, developed countries like Japan, Denmark, and places like that to the United States, the standard of living for the average citizen is equally as high, but the consumption of energy is like one-third. Now, regard to personal vehicles and things like that, again, I think many developing countries feel that they look to the United States as the example. Everybody owns a car, a big car sometimes, a couple of cars, a car per person sometimes, eats lots of meat. They aspire to all those American things, which we now are learning, eating too much meat is really not really good for your health. The younger generation of Americans are actually beginning to think, if you live in a metropolitan area, you may not want a car. So a lot of 25-year-olds and 30-year-olds I know, and 20-year-olds, you probably can't afford a car, but there's public transportation, but there's Uber, there's Zip cars, there's all sorts of other things. They don't want to live in the suburbs and spend 1 or 2 or 3 hours a day wasting their life commuting. And so there's a better realization that there's more to life than sitting in a commuter bogged down in traffic. But there's there are all these things that are possible, and I think it's also a massive public education campaign that we should be embarking on, just like we did with cigarettes, for the carbon problem, as well as there are all sorts of other problems. And because when you're older and you're adults, you have inbred habits, and it's harder to change. And so now, country like China they don't know what to do. There's huge urban sprawl. The traffic jams in Shanghai and Beijing are much worse than in Berkeley. Okay, they're terrible. And so there's an opportunity there to and the public transportation is so overly crowded, but and then you actually don't want electric vehicles. What you want are electric scooters, electric bicycles, electric things. Now the electric skateboards are a little bit too expensive, but they weigh 15 pounds. So you can take the electric scooter, the electric bicycle, and especially electric, you can take it in public transportation, you can put it, your knapsack, your electric scooter, you can take it home into your apartment and recharge it. So there are lots of things that this new technology will enable very crowded, overdeveloped cities to deal with, that you have to figure out how to get people to not just view the automobile and sitting in massive traffic jams as the ultimate status symbol. Okay, but it is at the moment.
How about the question over here at the other mic?
Thank you very much for your presentation and your sense of humor. I'm here with a number of women from Tech Women from Africa, Middle East, and Central Asia. And several of these women, wave your hands over there, are in solar. Do you have advice for them on how to help them grow their solar companies and get their governments more on board?
Yeah, I think in a lot of developing countries, first, if you have to compete with electricity generated by diesel, there is no competition. Solar is cheaper. You want diesel backup, maybe, but a lot of the things in a developing country what's the first thing people want in sub-Saharan Africa or South Asia? Is a cell phone. Has its own battery. You want clean lighting, LEDs, so you can read at night, not kerosene lamps. This is very bad for your health. Has its own battery. You would maybe want a refrigerator, but you don't really want the 20 cubic foot refrigerators with 4 cubic feet of freezer space. You just want to keep food fresh for a day or two. So you can get a better insulated refrigerator, and this little compartment, you freeze a block of ice, and it can keep it cool for a day or two. Now, when you have bad weather and something like that, you would need backup. But diesel or some other thing like that, it's the cost of the diesel is everything. So you can supplant a lot of, so think hybrid, water purification or water pumping. When the sun shines, you pump water. That's energy storage, and you can purify it. So many of the things aren't, you don't need a big enough battery to flick on a switch. And once you're competing with diesel, it becomes very cheap. And it's the lowest cost option at the moment. That's why Hawaii is kind of going a little crazy with solar, and so much so that the Hawaiian Electric Company wanted to put a moratorium on solar. No more solar. I think they wanted to put a moratorium when the integrated solar generation was, I think, 3 or 4%. But you can easily go to 34, 50% because electricity in Hawaii costs 40 cents a kilowatt hour. And so I think, India, Sub-Saharan Africa, South Asia, in many places, a huge opportunity if, you have space. And they're getting more robust. We should mention the battery. We don't have a lithium-ion battery that can stand unprotected summer heat. All right? Lead-acid battery doesn't have to be cooled, but there's been a nice, remarkable thing that's happening with lead-acid. Lead-acid can now, new technologies can now do deep discharges with lead-acid. Lithium-ion, if you're a Tesla owner or a Nissan Leaf owner, you park that car in an airport for a week unprotected, the car uses the battery to cool the battery so it doesn't go above a certain temperature until the battery's all discharged. And then you come back after a week or week and a half, it's dead, as in never to be revived. Okay? So that's one of the very visible targets that all the people who are in battery technology. You want a battery that works, doesn't need to be cooled in 100-degree weather. Okay? But there is a few other things. I'd be glad to talk to any young people, and if you want to, go into this field, there's a number of requirements. But solar is great, and the people who sell diesel and diesel backup are out there trying to convince people that solar is unreliable, so you shouldn't depend on it. They're actively trying to do this. And so, just think it may not be the 100% solution, but it could be certainly a 75% solution or a 50% solution.
Okay, we're going to take 2 more questions, one here.
My question is, do you still have the energy to win another Nobel Prize, either in your field or a related field?
Well, that's not why you do science. You do science because you love doing science. And do I have the energy? Yes. I still work 60, 70 hours a week. And so that's okay. And since I've gotten back, Stanford's applying for 4 patents. They'll probably need another 3. So there's some new ideas also in batteries and in biology. All I can say is serving the government for 430 years didn't suck out my vital juices. I wasn't sure whether it would or not. But once I got back and you had nothing else to do except think about stuff, all these new ideas started coming. So I'm happy about that. For all older scientists, in case you're wondering, will be 68 in February. And starting a new group when you're 66 from 0 is a daunting task, but it's a gas. I'm having lots of fun.
Last question.
Yeah, so Professor, so when we're dealing with the laser trapping or something like that, so how do you ensure your cell or microstructure not be burned by the laser?
Okay, so first, I'm not doing laser trapping anymore, but that's a good question for anything you're using light to shine into cells, because the light could induce some biology and undesirable biology, and ultimately, if it's a high enough intensity, it kills the cell. The laser trapping stuff is mostly done in what we call in vitro experiments, where you grab onto a polystyrene sphere and you're putting this thing away from the biological system. But if I would generalize to any new thing you do with any new technology, there's always a fear you've disturbed the system. The nanoprobes could distort the biology. Shining in we've learned over the last half dozen years that shining in a lot of light, the cells don't like it. But there are ways of doing that, of doing what are called control experiments, because in the end, what you really want to do is you're trying to report on what's really happening in biology. But that's true of most of the techniques in biology. Okay, you have to be very careful about whether you're really seeing what's really happening. But let me just tell you that I can't tell you how exciting it is and what's going to be happening in the next years and decades. Transformative stuff. A former student of mine, undergraduate and last year of graduate and postdoc, who's now at Stanford, Steve Quake, has developed ways of first, instead of amniocentesis to look at birth defects, you can take a little sample getting down to a pinprick, and you can fish out and you can identify the child's DNA from the mother's DNA. And it's as reliable and even more reliable than amniocentesis. So within 1 year in the United States, it's rapidly switching over. Then you can do it in organ transplants. it's different DNA. And so if you have a lung or a kidney or whatever, and they have to give the patient immune suppressant drugs, because once the body recognizes this is foreign tissue and begins to attack it, it's bad news. So for the rest of your life, you're taking immunosuppressant drugs. Kidneys the least amount, but when you're heart and lungs, it's a lot. Livers, okay. And now what we think will be able to happen is in the blood, if your body begins to reject, doctors used to wait for symptoms. But they would keep you on high doses, but once symptoms appear, it's dicey as to whether you can give enough anti-immune suppression drugs. And they wait for symptoms, and let's say it's a heart transplant, they'll stick a needle into the heart and slurp out some stuff. It's painful, it's expensive. And this is going to be replaced by a pinprick. So every week, you can prick yourself in a doctor's office. Oh, by the way, it's going to be doctor's office. Doesn't have to go to central lab. You can monitor yourself. You go way down in immune suppression. There's other things, cancers. I'm working with a colleague, I didn't talk about this, where lots of stuff gets misdiagnosed early on. And it's a painful, sad thing of, we all have loved ones that get misdiagnosed and finally it becomes overwhelmingly apparent that something really bad is happening, and many times it's too late. And so there is a very strong possibility because in a cancer that's recurring and metastasizes, it's in the bloodstream, and there's free DNA in the bloodstream. And we know, let's say, half the human cancers are related to a set of mutations in one molecule, and there are about 30 major mutations that you can put on a gene chip, and you can look for those mutations. And again, it becomes a pinprick. Okay, so in the next decade, I'm pretty confident that a lot of the early misdiagnoses can go away. And when a cancer comes back, you can find it early, and then you can deal with it. And when the cancers actually develop and mutate, they become different types of cells. And again, we're with the same person. We're working on, can you find a millimeter or submillimeter cancer that's metastasized, and you can locate it, and you can take a needle biopsy, slurp it out, do the DNA testing to see how it's mutated, to what drugs would be more effective or not. This is really exciting stuff. And I am confident, whether it's a decade from now or 5 years from now or 15 years from now, it's happening as we speak. So, the immunosuppressant stuff that got the Lasker Award this year, it's fantastic. You can target the cancer cell, and the cancer mutates, but your immune system keeps up with it. And so as it mutates and goes and looks like a Darwinian evolution, your immune system is keeping up with it, and the most effective treatments are the ones that are the deadliest that mutate the most, because it keeps the immune system on alert. So if you can, and I'm trying to work on the imaging part of this, so you can find it and then get a little slurp and see what's happening. So, it's a little piece of the big part I'm trying to do, but it's really exciting what's happening. It's really exciting what's happening in renewable energy and batteries. So I'm excited to be, alive and well, so to speak. And it's very exciting. So I think I've lived there long enough.
Perfect note to end on. So let's thank Steve Chu.